Allylic and benzylic radicals. An allylic radical is something which has an unpaired electron on the allylic carbon, whereas a benzylic radical has an unpaired electron on the benzylic carbon. One important thing to say about this allylic and benzylic radical is that it can have resonance contributor. Say for example, the bond right here can break and it can actually try to form another pi bond, and the other electron is going to switch onto the other carbon, which is going to result in the other resonance contributor. So this is the structure of the other resonance contributor. And similarly, benzylic radical can have phi resonance contributor, where the electron right here can come in together to form a pi bond. Okay, and there is a new radical that has been created. So let's draw the structure here. So likewise, the electrons right here can hop in together around the aromatic ring to give the phi resonance contributors. And here are the phi resonance contributors for benzylic radical. Now let's go on to the relative stabilities of the radicals. Now that we have added two more radicals, benzylic and the allylic radicals, we needed to place them in the order of stability of the radicals. In general, the benzylic and as well as the allylic, they are going to be much stable than the tertiary, secondary, primary, vinyl, and methyl radicals. Now, the reason behind it is because of the resonance contributors that it can exist as. Okay, so remember, the benzylic radical can exist as 5 resonance contributors, and the allylic radical can exist as 2 resonance contributors. Because of the extra stability, they are going to be more stable than the rest of the alkyl and vinyl radicals. Allylic bromination and NBS. What is NBS and what is it going to do? NBS is N-bromosuccinimide. Here is the structure for N-bromosuccinimide. N-bromosuccinimide is used to brominate allylic carbons because it allows a radical substitution reaction to be carried out at low concentration of bromine and HBr. If we are going to use high concentration of bromine, then the addition reaction is going to take place at the double bond. Okay, say for example, if we are going to add high concentration of bromine and HBr, there will be addition reaction where the bromine and the HBr is going to get added to the double bond. But we don't want that. We want the allylic hydrogen to be replaced with the halogen, for which we use N-bromosuccinimide. And in order for this reaction to take place, we have to have heat or light and also a radical chain initiator, peroxide. So the product here is going to be 3-bromocyclohexene and also succinimide. Let us now look into the mechanism for allylic bromination. The first step, N-bromosuccinimide is going to cleave homolytically at the NBr bond. Let's draw the structure for N-bromosuccinimide. The NBr bond is going to cleave homolytically, where one of the electrons is going to go on to bromine and the other electron is going to go on to nitrogen, thereby forming the two free radicals. Now in the next step, this bromine radical is going to react with a compound. Let's say that we want to do the allylic bromination on a propene molecule. Here is our propene molecule. Okay, the first step here in the propagation is going to be where this bromine radical is going to go remove the hydrogen from the propene molecule. Okay. Thereby giving us an allyl radical and also HBr. But remember, this allyl radical can be in resonance with the other resonance contributor. So here in this case, the two resonance contributors are equal. Now in the next step, this allyl radical which is created is going to react with bromine molecule. How did we even get the bromine molecule? Bromine molecule is formed by the ionic reaction between N-bromosuccinimide and HBr. Okay. So let's write down the equation for that. N-bromosuccinimide undergoes an ionic reaction with HBr, which is going to give us succinimide and bromine molecule. So our formed allyl radical is going to react with a bromine molecule, where the weaker sigma bond between the bromine and bromine is going to break, and it's going to try to form a bond between carbon and bromine. So here is our product that is formed. This is a product that we wanted. Okay, the last step is determination. Now let's identify what are the different radicals that are created. We have a bromine radical that's created, and we also have an allyl radical that is created, right? In the termination step, two bromine radicals can come together to form the bromine molecule, and two allyl radicals can come together to form a bond between carbon and carbon, to form a sigma bond between carbon and carbon. And an allyl radical and a bromine radical can come together to form a compound. The allylic brominations can sometimes give rise to two different products depending upon the type of resonance contributors that it is forming during the process. Here is the situation. We have a bromine radical that is reacting with cyclohexane. Here in this case, it's going to be only one product. But when you take the substituted cyclohexane, there is a possibility that it can give you two products because the two resonance contributors are different. Okay, now let's find out what is the product that we'll be getting for this. Okay, remember this carbon right here, these two carbons right here is allylic carbon, but this structure is symmetrical. So abstracting any one of this hydrogen, or removing any one of this hydrogen is going to result in exactly the same allylic radical, right? So this is a radical that is formed in the first step. And this radical is going to be resonance stabilized with the other resonance contributor, where it results in a new pi bond and a new radical at a different carbon, right? But when you take a close look into these two compounds right here, these two radicals are exactly the same, right? So whether the bromine goes and gets added to this carbon or it gets added to this carbon, it's going to result in exactly the same compound, which is 3-bromocyclohexane. Because the reason for the formation of one compound is it resulted in the two resonance contributors that comes from here, or they are exactly one and the same. Now let's go on to the second reaction. Here we have a bromine radical that is reacting with substituted cyclohexane. Here in this case, there is a chance that it has the ability to form two different resonance contributors. Okay. So to begin with, this is our allylic carbon, and we know that there is a hydrogen here. In the first step, this hydrogen is going to be removed, and there should be a radical on that carbon, right? So if you want, you can show the hydrogen here, and the bromine radical is trying to pull this hydrogen off, trying to form the radical. So this is the new radical that is formed. This is going to be in resonance with the other resonance contributor, where this electron is going to hop in here to form a new pi bond, and new radical is created. Now the bromine radical has got two chances. It can go and add to this carbon, or it can go and add to this carbon, and accordingly two different products are obtained. So here are the two different products, and you can see the reason behind these two different products is because they had two different resonance contributors to begin with. Let us now do an example in the allylic bromination using NBS. Two products are formed when methylene cyclohexane reacts with NBS. Show how each of these compounds are formed. Okay, in the first step, we have to find out the allylic carbon and remove the hydrogen that is attached to it. Okay, here is our allylic carbon, and we know that there are two hydrogens on here. With the use of bromine radical, we are going to remove one of these hydrogens. Okay, so in the first step, the bromine radical will remove one of these hydrogens. Okay, thereby creating an allyl radical. This is our allyl radical that is obtained. And in the next step, when the bromine radical comes in, tries to form a bond here or gets added to this carbon, then this is the product that will be formed, right? Okay, but remember this allyl radical can also be in resonance with the other resonance contributor, where this electron can hop in here trying to form a new pi bond, and the electron, one of the electrons from the pi bond is going to go to the other carbon. Okay, so thereby creating another allyl radical. So this is our another allyl radical. Now the bromine radical can come in and add to this carbon which has this radical and form this compound. Okay, so there are two different compounds that are obtained here because there are two different resonance contributors.